In this video, we're going to talk about determining empirical and molecular formulas from elemental composition data. So in our first problem, elemental analysis was performed on 25 milligrams of a sample of a compound, and the following elements were recovered in their amounts: 16.36 milligrams of carbon, 2.29 milligrams of hydrogen, and 6.36 milligrams of nitrogen. So what is the empirical formula of the compound? Right? So I'm going to transfer these to a new page so we have room to work. So here is our transferred information. We have 16.36 milligrams of carbon, 2.29 milligrams of hydrogen, and 6.36 milligrams of nitrogen. Now remember, the empirical formula is the simplest ratio of atoms, and it's also the simplest ratio of moles. And so we can use these amounts to find the moles of each one to approach the ratio of moles that will give us the empirical formula. So we can start with our 16.36 milligrams of carbon times 1 millimole of carbon atoms is 12.01 grams of carbon. And that gives us 1.3622 millimoles of carbon atoms. So then we take the 2.29 milligrams of hydrogen recovered times 1 millimole of hydrogen atoms is equal to 1.008 milligrams of hydrogen. And let me make clear up here, that I got my units correct up here. That should be milligrams of carbon atoms to be consistent. So now when we go back to our hydrogen, we get 2.272 millimoles of hydrogen atoms. And then we have 6.36 milligrams of nitrogen. We know that 1 millimole of nitrogen atoms is 14.01 milligrams of nitrogen, and that gives us 0.4540 millimoles of nitrogen. So we've got these. Now we've got a ratio here, but it's not a simple whole number ratio. So how do we turn this set of data into a simple whole number ratio? So here are those results. In a simplest whole number ratio, the lowest number that a number can be is 1. So the easiest way to make our lowest number 1 is to divide it by itself. And so we're going to divide all three of our results by our lowest result. So let's move these where we have some space to work. And so we're going to take our 1.3622 millimoles of carbon and divide it by our 0.4540 millimoles of nitrogen. And that gives us 3.00 millimoles of carbon per millimole of nitrogen. And we're going to take our 2.272 millimoles of hydrogen and divide it by our 0.4540 millimoles of nitrogen. And we get 5.00 millimoles of hydrogen per millimole of nitrogen. And then, of course, if we divide this by itself, we get 1 millimole of nitrogen per millimole of nitrogen. Well, now we have nice, simple, whole numbers. And so now we can say that the overall formula for this is, right, there are 3 carbons, 3 moles of carbon, for every 5 moles of hydrogen, for every 1 mole of nitrogen. But of course, if it's 3 moles to 5 moles to 1 mole, then it's 3 atoms to 5 atoms to 1 atom. We cannot simplify this anymore, and so that becomes our empirical formula. So that is how we approach finding an empirical formula. We found the empirical formula of the compound. Now can we find the molecular formula of the compound if it's different from the empirical formula? Well, in order to do that, we need another piece of information. To find the molecular formula, we need the molecular weight. So let's assume that someone took this compound and submitted it for mass spectrum analysis to determine the mass and found out that the molecular weight of our compound is 165.24 atomic mass units. Now, how can we use that to find the molecular formula from the empirical formula? Well, the first thing we need to do is find the empirical formula weight. So we take, right, our formula, and we have 3 carbons. That would be 3 times 12.01 atomic mass units, right, per carbon, which would give us 36.03 atomic mass units. And then we have 5 hydrogens in our formula. That's going to be 5 times 1.008 atomic mass units per hydrogen. That gives us 5.040 atomic mass units. And then we have 1 nitrogen. That's 1 times 14.01 atomic mass units per hydrogen. Gives us 14.01 atomic mass units. Right? Our answers are all in atomic mass units, so we can add those numbers and get something in atomic mass units. And so we get, right, 8, 0, 6 and 4 is 10 and 5 is 15, 4 and 1 is 5. 55.08 atomic mass units. Okay? So this is our empirical formula weight. This is our measured molecular weight. They are different, and so the empirical formula is not the molecular formula. Now, how do we find the molecular formula? So here's our important information carried to a new page where we have room to work. We found out our molecular weight is 165.24 atomic mass units. Our empirical formula weight is 55.08 atomic mass units. And the empirical formula is C3H5N. Okay, now, what we want to know is how many empirical formulas we need to take. How many times do we need to multiply this to get that? And so the easiest thing to do is take that divided by that. And let's put appropriate units on it. Right? So if we take our 165.24 atomic mass units per molecule, right, the whole molecule, and divide that by 55.08, and I don't like my 55, let's write that again, 55.08 atomic mass units per empirical formula. When we do that math, we get 3 empirical formulas per molecule when our units cancel, right? When we divide, we invert and multiply, so the empirical formula ends up in the numerator. The atomic mass units divide out. Since we're dividing here, this ends up in the denominator, so we get this many empirical formulas to make a molecule, right? So we take our formula, C3H5N, and we multiply that by 3, right? Empirical formulas per molecule. And that gives us C9H15N3, and that is the molecular formula. Right. So you need to practice that because that is something that you will need to be able to do. Okay, let's change our situation a little bit. In our last problem, we didn't know our molecular weight until after we had determined the empirical formula. Now we have the molecular weight from the beginning. And elemental analysis not given in mass, but in percent. So we have a molecule that has a molecular weight of 144.22 atomic mass units. And the results of elemental analysis tell us that it's 49.97% carbon, 11.18% hydrogen, and 38.85% nitrogen. And then we need to determine the molecular formula of the compound. So there are 2 ways we can approach this, and you can do whichever makes sense to you. But method 1 is assume that we started with 100 grams of the compound when we did the elemental analysis. And so we can use these percentages to determine our starting masses, right? So 49.97% of 100 grams is 49.97 grams of carbon. And 11.18% of 100 grams is 11.18 grams of hydrogen. Right? And 38.85% of 100 would give us 38.85 grams of nitrogen. Now we can use these as our starting masses and work the problem just like we did the last one. So we've brought those numbers forward onto some clean workspace, right? And so we find the number of moles. Again, right, a formula is going to be a mole-to-mole ratio. So let's start with moles if we can't find atoms, right? So we're going to have 1 mole of carbon is 12.01 grams of carbon. Note, we're in grams instead of milligrams here because we've got more material. And that's going to give us 4.1607 moles of carbon, right? And I'm keeping extra decimal places because I'm not at the end of my calculation, right? So significant figures are not an issue at this point, right? And then we're going to have 1 mole of hydrogen atoms is 1.008 grams of hydrogen. And for that, we will get 11.0913 moles of hydrogen atoms. And then 1 mole of nitrogen atoms is 14.01 grams of nitrogen atoms. And we get 2.7730 moles of nitrogen atoms. Again, we've picked a compound where there's the least number of moles of nitrogen. And again, the smallest a number can be is 1, right? So what is easiest then would be to divide everything by the number of moles of nitrogen. Right? And so if we divide the number of moles of carbon by the moles of nitrogen, we get 1.5 moles of carbon per mole of nitrogen. For hydrogen, we get 4 moles of hydrogen per mole of nitrogen. And for nitrogen, of course, we get 1. Okay, now, this time we didn't get simple whole number ratios. We've got this thing that is a half, right? And so that makes it difficult to deal with, right? We can't just round off a half an atom. We can't gain or lose half an atom. So this is where it takes a little feel. Is it a half an atom? Is it a third of an atom? Is it 2/3? Is it a quarter? Right? So here we have a half. The easiest way to get rid of a half is to multiply by 2. So if we take our 1.5 moles of carbon per mole of nitrogen and multiply that by 2 moles of nitrogen, we get 3 moles of carbon, right? And if we do the same thing for our, I'm running out of space here, 4 moles of hydrogen per mole of nitrogen, and we multiply that by 2 moles of nitrogen, we get 8 moles of hydrogen. And if we take our 1 mole of nitrogen per mole of nitrogen and multiply that by 2 moles of nitrogen, we get 2 moles of nitrogen. Right? Now we have a different ratio, 3 to 8 to 2. So we can write our formula as C3H8 N2. And at this point, this is an empirical formula until we check it against our molecular weight. Right? So we'll move to a new page to do that. So we transfer our important information to a new workspace. Right? We've got the empirical formula we just determined, and we've got the molecular weight that was given in the problem. Right? So we need to find an empirical formula weight. See if it's the same as the molecular weight. Okay, so that's 3 times carbon, which is equal to 3 times 12.01 atomic mass units. That's 36.03 atomic mass units. And that's, right, 8 times hydrogen, which is 8 times 1.008 atomic mass units, which gives us 8.064 atomic mass units. And then we have 2 times nitrogen, which is 2 times 14.01 atomic mass units. That gives us 28.02 atomic mass units. Right? When we sum that up, 41127 atomic mass units. So, our empirical formula weight does not match our molecular weight. Right? So that is not the molecular formula. So we need to find out how many times we need to use this empirical formula to make our molecule. And so we take the molecular weight, 144.22 atomic mass units per molecule, and we divide that by 72.114 atomic mass units per empirical formula, and that tells us that we have 2.00 empirical formulas per molecule. Right? So we will take 2 times the C3H8N2 to get our final formula of C6H16 N4. And that is our molecular formula. Now, that completes method 1 of approaching this problem. Right? There is another way to do it that, depending on the question asked, can simplify your calculations, but it requires a little bit of a different approach. So let's look at the other approach to this same problem. So let's approach this same problem, right? We have the same molecule with the same molecular weight, and we have the same elemental composition, and we're going to determine the molecular formula of the compound. But this time we're going to do it without determining the empirical formula. Where last time we assumed we started with 100 grams of our compound, this time we're going to assume that we start with 1 mole of our compound, and that will change our approach a little bit. We bring forward our important information, right? Our molecular weight and our percentages of each element, right, in the compound. So, one of the things we have to remember, if we know the molecular weight, right, we also then know the, right, so therefore, 1 mole of the compound is 144.22 grams of the compound. Right? So we can use that. Right? If we start with 144.22 grams of our compound, and right, the percentage tells us that there's 49.97 grams of carbon for every 100 grams of the compound. And so we can use that to find that we have in a mole 72.067 grams of carbon, right? And we have 144.22 grams of our compound, right? And the percentage tells us that there's 11.18 grams of hydrogen per 100 grams of our compound. And that tells us that then we get 16.124 grams of hydrogen. Right? And again, if we start with the same mole of compound, which is 144.22 grams, right? Then we have 38.85 grams of nitrogen in 100 grams of the compound. And so we have 56.029 grams of nitrogen. Right? So now we have the amount of grams of each element that is in 1 mole. Right? That gets us closer to what we want to be. We're closer to that, using that law of specific proportions to our advantage. So here are our results, right? Transferred over. So now we know to build a formula, we have to go from grams to moles, because moles are proportional to atoms, right? And so we take our 72.067 grams times 1 mole of carbon per 12.01 grams of carbon, and we get 6. moles of carbon. And we take, right, we know that 1 mole of hydrogen is 1.008 grams of hydrogen. And if we do that division, we get 16 moles of hydrogen. And if we take our nitrogen, we know that 1 mole of nitrogen atoms is 14.01 grams of nitrogen atoms, and that gives us 4. Okay. That is a simple whole number ratio, C6, H16, N4, right? Which we've seen before. If we add that up, right, the formula weight is equal to 144.82. Therefore, that is the molecular formula. Right? So, if you're given amounts, you can go through moles, find the empirical formula first, then use the molecular weight to find the molecular formula. Right? If you're given a situation where you're given percentages, you can either go that way, or you can apply the percentages to the molar mass, and then your results come out directly in the number of moles of each element in a mole of the compound, which leads directly to finding the molecular formula. Right? So you have 2 ways of approaching those problems. And you should be comfortable doing either one. Okay, so here's our third different problem, right? We have an ionic compound, and it has a composition of 49.67% vanadium and 50.33% phosphorus. So we have to determine the empirical formula for the compound. Remember, for an ionic compound, something containing a metal and a nonmetal, or a metal and an oxyanion, the empirical formula is the fundamental formula unit, right? So that is the proper formula for this, right? So let's remember, right, if we've got something given in percentages, we can assume that we are going to start with 100 grams of material. So that would be that we would start with 49.67 grams of vanadium in that 100 grams. And we would start with 50.33 grams of phosphorus in the 100 grams of starting material that we analyzed, that we assumed we analyzed. Right? And so we look on the periodic chart and find that vanadium has an atomic mass of 50.94 atomic mass units. Therefore, 1 mole of vanadium is 50.94 grams. And if we multiply that out, you get 0.9751 moles of vanadium. Right? So we look on the periodic chart at phosphorus. We find out that the atomic mass of phosphorus is 30.97 atomic mass units. Therefore, 1 mole of phosphorus is 30.97 grams, and we get 1.6251 moles of phosphorus. Right? Okay, so our number of moles of vanadium is the smaller number. So let's divide both numbers by that. So we have our 1.6251 moles of phosphorus divided by 0.9751 moles of vanadium, and we get 1.6667 moles of phosphorus per mole of vanadium, right? And obviously then we get 1 mole of vanadium per mole of vanadium. So let's take those numbers to a clean workspace. So here are our numbers brought forward, right? And so if we look at this, this is again where a feel for numbers helps us, right? That is about 1 2/3 mole of phosphorus per mole of vanadium, which if we expand that is equal to, right, 5 moles of phosphorus per 3 moles of vanadium, right? And so, right, if we multiply this by 3/3 to make the denominators the same, we get 3 moles of vanadium per 3 moles of vanadium. But the important thing is 5 to 3 is a simple whole number ratio. Now, remember when we write the formula for an ionic compound, the metal goes first. So we get vanadium 3, phosphorus 5 as the formula. And since that empirical formula is the fundamental formula unit, we can actually name that, right? So we know by looking at the periodic chart, phosphorus tends to make a 3- ion. So 3- times 5 is 15-, which means vanadium has to make up 15+, and that has to be divided among 3 vanadiums. That's going to be 5+ per vanadium. And so we know vanadium has a charge of 5, and so now we know this compound is vanadium 5 phosphide. Right? Right? So with an ionic compound, the empirical formula is the fundamental formula unit. And so we can use that, right, to determine the final relative formula, and then we can name that. Right? So there's a lot we can do here with these problems. I've given you 3 different problems and 4 variations of approach. You should be comfortable with any of them and apply them to appropriate problems.